In this section, we discuss the extrema on an interval, the extrema or the maximum or the minimum values of a function on an interval, whether it be a closed interval or an open interval. I'm wearing this hat because I want to, and my barber messed up my line, and I gotta go get a haircut today. So that's the real reason. I don't want to wear this hat, but I called my barber and told him that I'm hurt that he messed up my hair, and I don't have much up top anymore, and so I've been trying to keep it for a little while. But anyway, the extrema of a function. This section, and not just this section, but this entire chapter is devoted to examining functional behavior to be able to investigate the so-called maximum value, whether it be relative maximum, relative minimum, or the absolute minimum or the absolute maximum. How we're able to calculate that by first examining what we call a critical value by looking at the first derivative. And then from there, the sections as we progress, we will talk about certain techniques to be able to determine the intervals by which the function is increasing, the interval by which the function decreases. From there, to look at the first derivative test to be able to investigate the extrema. And then also for concavity, how the curve or the curvature of functions, how that is exhibited, and then from there to look at the second derivative test. But today we start with the preliminary, and we discuss the so-called extrema of a function. We say that if f is defined on some open interval I containing a point c, f of c is the minimum value on this interval, whereby we say f of c is less than or equal to f of x for all x in the interval, or f of c is said to be the maximum on the function f on this interval I if f of c is greater than or equal to f of x for all x in I. We can talk about the so-called extrema here in terms of absolute or in terms of relative. To say that we have an absolute maximum or absolute minimum really means that the interval by which you are examining is said to be closed or all inclusive of the points. If you can include the endpoints, then you can determine exactly if that particular function on that interval is said to have a so-called absolute minimum or absolute maximum. Sometimes a function may not have what we will call later a relative extrema, that is a relative max or a relative minimum. That simply means that you're looking for a local minimum contained within an interval. But to include the endpoints, you might not have a local minimum or local maximum or relative, that is, but you may have an absolute. Sometimes that is with respect to linear functions, a straight line function, where there's no curve to denote that at the top of this curve, we crest it out, we have a maximum, or like in the valley low there in that curvature that concaves upward, I have a relative minimum. But what if it's a straight line, and if it's a slope that's not zero or a slope that's not defined, then you do not have a relative minimum or maximum for a straight line. But if it's on an open interval, but if it's a closed interval, you talk about the absolute relative, the absolute extrema, and that would be possibly the endpoints. And we'll look at an example of that as we proceed. So if we have this function here, and this curve, f of x is x squared plus 1, looking at the closed interval from -1 to 2, then if you include the endpoints, where the endpoints here are included, -1 and also the +2 is included, then you can pinpoint here minimums, which the minimum here would be at 0, 1, and the maximum for this particular function occurs at the endpoint where x is equal to 2. So there we say that 2, 5 is an absolute maximum. 0, 1 is here said to be relative. It is a minimum, but and the neat thing about the so-called extrema is that you talk about a relative extrema versus an absolute extrema, and particularly with respect to if the interval is closed or open. Well, we'll talk more about that and get more specific about it as we move a little bit later on. Here, this function is continuous for this problem, but the interval is said to be open. And so the point 2, 5 is not included because 2 is not included on the interval. So here 2, 5 is not a maximum. But since 0, 1 is contained within the interval from -1 to 2, then 0, 1 is still set to be a minimum. If g is defined as a piecewise function, where when x is equal to 0, we get a different value for g, here is said to be 2. So that means that you do not have a minimum anymore, but you do have a maximum because the function is said to be closed from -1 to 2. The extreme value theorem given to us by Fumet himself. If f is continuous on a closed interval from a to b, and the key is that the interval is closed, that's the key, then f achieves, according to the old language, f achieves what the theorem actually says, that f achieves an extrema. But here, for your sake, we try to simplify that and say f has both a minimum and a maximum on the interval. Okay. Now, the relative extrema is simply talking about the maximum or the minimum on an open interval. The critical numbers are crucial because the critical numbers they come on the idea that when I set the derivative equal to 0, that derivative then is said to crest it out because the derivative is a tangent. And if the derivative is set to equal to 0, then at that tangent is horizontal. Remember that the derivative is a slope, so if the slope is equal to 0, isn't that a horizontal line? All horizontal lines have 0 slope from arithmetic. So we define a relative extrema. Notice that the relative extrema is defined on an open interval always. So if there's an open interval containing C, on which f of c is a maximum, then f of c is called a relative maximum of f, or you can say that f has a relative maximum at the point c comma f of c. Likewise, the same argument for the relative minimum. Relative extrema and relative maximum are sometimes called local extrema. So a local maximum or a local minimum. That is that a function may have more than one relative extrema, but a function will only have one such absolute maximum or one such absolute minimum, but the absolute nature occurs on closed intervals. So here for this function, f has a relative maximum at the origin 0, 0, and it has a relative minimum here at the point 2, -4. This is interesting. F prime of 0 does not exist, but it is possible to have a so-called relative extrema at that particular point. Here, f prime of 3 is equal to 0. That means that it crests out that is, it tops off there and it goes back down, or you could crest it below like in a valley and have a tangent. So there, that's what it means when you say f prime of 3 is equal to 0. Here we have a horizontal line. That point here, the critical number is x equal to 3. It's a critical value. Definition of critical values. If f prime of c is equal to 0, then we say that c is a critical number. Here's the thing, that you could have f prime of c equal to 0, or f is not differentiable at c. Then f is said to have a critical value at c. When is it that the derivative does not exist at a point x equal to c? Well, that simply means that the function is not differentiable if you have a spike, sharp turn uh, at a particular value, or even a jump. But here, not differentiable simply means sharpness or a spike. And here, for this first graph, there's a spike there, right? Here, f prime of c is equal to 0. That always means you have a horizontal tangent. If you have a horizontal tangent, that means that the curve is cresting it out. C is said to be a critical number if f prime of c does not exist, or if f prime of c is equal to 0, one or the other. So the relative extrema occur only at critical numbers. If f has a relative extrema at x equal to c, then c is called a critical number. And then here are some guidelines for us to being able to determine the extrema on a closed interval. Basically, what we're going to do is you can find the critical numbers, that is, set the derivative equal to 0, the first derivative, evaluate f at the so-called critical number, and then evaluate f at the endpoints. Uh, the least of these values is set to be the minimum, the greatest is the maximum. And typically what I do is to, if I can graph the function here, since we have not been introduced the first or second derivative test, graph the function, and then from the function's graph, you should be able to determine the absolute extrema. Next, we'll look at some problems.